It is 5:17:17. So we're going to do kind of a highlights reel on chapter 13. This is all about solutions. And a solution is a mixture. It's a special kind of mixture. We talk about substances being soluble, and something is considered soluble when it can be dissolved in another substance. So when we dissolve something, we take its solid form, and those particles leave their solid form, and they become uniformly distributed into a liquid. That's the most common definition of a solution, though there are solutions that are not liquids. We'll get to those in a little bit. When a soluble substance is dissolved into a liquid, a solution is formed. Okay, we can read. What a solution is at its heart is a homogeneous mixture of two or more substances. And they can be in multiple different kinds of phases. Okay. Two pieces make up a solution. The solvent, which is what does the dissolving, and the solute, which is the thing that gets dissolved. In salt water, which is the solvent. If I make a solution of salt water, sodium chloride and water, which the water is the solvent, it's doing the dissolving, the salt is the thing that is dissolved. This gets a little bit trickier if we're talking about solutions made up of two liquids, or solutions made of two solvents, or I'm sorry, two solids, or gaseous solutions, because we can have those too. In the case, it's really easy if you have a solid and a liquid. The liquid's the solvent. In cases where that is not true, the thing that there's less of is what we consider to be the solute. So you're sitting in a solution right now. The air around you is a solution of multiple gases. They are evenly distributed. In that case, I suppose we could call nitrogen the solvent, and all the CO2 and the water vapor and everything else the solutes, because those are the things that they're smaller components of the mixture. So why are we doing this at all? Why rush through chapters 12 to get to 13? To do chemistry beyond this, you really have to be familiar with some aspects of solutions. Most chemistry is done in aqueous solutions, and you've seen that this year. We've used a lot of things that are in aqueous solution. So it's important on that ground. By the end of this chapter, and I said we're doing the highlights reel, we're not going to do every piece of the chapter, but the things that you need to be able to do are distinguish when something is a solution, which is the solvent, which is the solute, is it saturated or unsaturated, and then talk a little bit about concentration. Those are the things that you're going to have to be able to do by the end of this unit. And you will, I promise. So, whoops. Okay, so I alluded to this before, but you can have a solution in any phase of matter. The key to it being a solution is that the particles have to remain in solution once they're dissolved. So we don't get areas where the carbon dioxide has settled out of the air. It all stays suspended. If you have made Kool-Aid, you don't go into the kitchen and find that all the sugar and the coloring has settled out. So it is a solution by virtue of the fact that it stays suspended. If you are wearing jewelry right now, it is probably a solution of solids. Most jewelry is not a pure metal. Gold is rated by its carats. And what is it? The higher the number, the higher the percentage of actual gold. The lower the number, the lower the percentage of actual gold. So 24 karat gold is nearly pure gold. It's very soft. Gold's too soft to wear well as a metal, so we tend to put other metals that are a little bit harder into it, like 18 karat gold has some other metals in it. We use things like brass a lot, bronze, pewter. Pewter is, if you have pewter at home, pewter dishes or pewter figurines, they used to have a high lead content. They used to be tin, copper, and lead. Modern pewter figures do not have the lead in them; they're tin and copper. So, but those are all solutions. When it's a solid solution, we call it an alloy, and typically what we see are alloys of metals. Okay, we have one other case which is called a suspension, and a suspension is not a solution. Who here has played in mud water? I am assigning homework if you have not. So if you take a big mason jar and fill it with muddy water, and you leave it to sit for a while, what's going to start to happen? going to settle. First, the larger particles, the sands and little tiny rocks that might be stirred up, and it will settle. Eventually, the clays and the fines will start to settle out of it. The water will probably never completely clear, depending on how fine the particles are, but it will settle. And water in a creek or a pond is the same thing. That's what's called a suspension. And in a suspension, particles will eventually settle. You have to keep agitating them to keep them sort of appearing to be dissolved. They're really never dissolved because they will never stay on their own. Mud water or clay water is the best example of a suspension we have. Your book gives a couple others. Okay, this is a weird one. Colloids have particles that are larger than a solution, smaller than a suspension. They do stay in suspension on their own, but they are not truly a solution because the things are not truly dissolved. The solids are still there, they're just dispersed and held. And the thing that tells you it's a colloid is what's called the Tyndall effect. If you shine a light through it and it looks cloudy, that's a suspension, or a colloid rather. Fog is a colloidal suspension of water. Colloids are sometimes called colloidal suspensions. Colloidal suspensions do not look clear, they look cloudy. Gravy is a colloidal suspension of starch particles. So the broth is clear, magically you put cornstarch in it and you boil it, and you turn that into a colloidal suspension. I believe Jell-O is also a colloidal suspension. No, it wouldn't be because it's clear. There's no light scattering. But the Tyndall effect is light scattering. The particles are dispersed enough that they catch and reflect light and scatter it, so the whole thing looks cloudy. Okay, this is one that we're going to talk about more in the next chapter, and we are going to do sort of 1.5 more chapters after this. An electrolytic solution is a solution that conducts electricity. We've talked about this a little bit. When we talked about ionic versus molecular compounds, we said that solutions of ionic substances tend to be conductive because those charged particles separate, and then you've got electrons that are free to move around. Any substance that can be dissolved in water that yields ions is going to conduct. So salt, table salt, sodium chloride, potassium chloride, sodium nitrate, anything that you can write an ionic formula for is going to be conductive as a solution. If it doesn't conduct, if it yields molecules, it's non-electrolytic. And so for the most part, ionic compounds are the ones that are electrolytic. There are a few exceptions to that, like acids. Okay, you know this stuff? Who here has made Kool-Aid? Excellent. What do you do to make the sugar dissolve faster? Stir it. Okay, agitating the solution. What else do you do to make it dissolve faster? Use hot water instead of cold water. Higher temperature actually makes things dissolve faster. What else can you do? What if you have chunky, lumpy sugar? Well, you stab it, you Alfred Hitchcock it, because what you're doing is increasing the surface area of the particles that are going to come in contact with water. Here's the thing. All of these things are, in essence, doing the same thing. What are they doing? They are increasing the number of collisions. Okay, so let's think about this all in terms of kinetic molecular theory. So you have this chunk of solid that you've dropped into liquid. There are particles in both of them. In the liquid, in the water here, the particles in the water are moving faster than the particles in the solid. The particles in the solid are just kind of sitting here. Imagine that this is bumper cars, and you are in the car out in the middle of the bumper cars that dies. What's happening to you? You're getting collided with by particles that are in motion. You're not really in much motion, but other particles are, and so they're running into you perpetually. Gets rather irritating. This is what's happening with this solid. So you've got particles from the water striking it because they're in constant motion. Every time they strike it, they have the opportunity to dislodge one of the particles from that solid and kick it out into solution. Now, the more strikes you have, the more energy you have to transfer, the more likely you are to get all of that solid dissolved. If you heat it up, the water molecules move faster. More opportunity for collisions. So that's how that one works. If you break this chunk up into smaller chunks, you are now increasing the number of particles of that solid that the water can possibly come in contact with. And again, you're increasing the rate of collision. That's what this is all about, is increasing the rate of collision. So anything you can do basically to increase the rate of collision, because it's all down to kinetic molecular theory. If you stir, so I'm going to put a spoon in there. There's my very badly drawn spoon. If you stir this solution, what are you doing? You're increasing the kinetic energy of the particles. You're basically offering more opportunities for collision. This is the last concept we'll talk about today. It is solubility. Solubility is the characteristic of how much stuff you can dissolve in a given solvent. And we're going to look at solubility tables for a couple different ionic compounds. We started to work with these when we were doing our crystal growth stuff earlier in the year. There is always an upper limit to how much stuff you can get into a given amount of solvent. Who here has made hummingbird food? Okay, so with hummingbird food, you put basically a 5-pound bag of sugar into some water, and you heat it until it goes clear and it's all dissolved, and then you cool it down and put it outside. What you are doing is saturating that solution. You're putting as much sugar as you can possibly get into that amount of water into the sugar, and you're actually adding a little bit more because of the fact that you heat it up. So there's always an upper limit. We use a solubility table to help figure that out. In any solution, whether it's reached that max or not, remember we talked about phase change equilibrium? You have particles coming into the gaseous phase and re-entering the water phase. Well, in solution equilibrium, guess what? Same idea. Here's our solution. So, there might be a lot of the particles that are spread out, but there are some that aren't. There are some that are still in the solid phase. At every moment, there are particles that are breaking free of that solid, and there are particles that are getting sucked into the attractive forces of that solid. The point at which that's happening at the same rate, we say we're at equilibrium. And we call it dissolution and recrystallization. So dissolution is the act of that solid dissolving. Recrystallization is the act of those particles that are in solution rejoining the crystal solid. Okay. You will have a quick video assigned tonight. The simple concept with solutions is saturated versus unsaturated. So, a solution that has as much solute as it can possibly hold is saturated. A solution that can still absorb more solute and dissolve it is unsaturated. Pretty easy. What we were doing with our crystal formation was making what are called supersaturated solutions. Now that, my friends, is a little bit different. So this is where we will end. When we get a solution that contains more solute than a saturated solution, under the same conditions but nothing's coming out, no crystals are magically falling out of it, that is a supersaturated solution. And the sources all say that a supersaturated solution can rapidly recrystallize, but we have yet to see evidence of that. It's not as easy as they say it is, unfortunately. So, I'll assign a little video for tonight, and I'll assign some homework problems, and that's it.